So there will be no final exam, and therefore there's no additional material to be covered. I just wanted to finish up today the chapter about activated carbons and porous carbon materials in general by talking about an application of activated carbons, which is the application is supercapacitors, which is an energy storage concept. So before we actually go to supercapacitors, let us briefly talk about capacitance in general. So what do we mean by capacitance? So generally, capacitance is the ability to store charge without the involvement of an actual redox process. So now no electrons will be permanently transferred from one atom to another atom, thereby changing the actual redox state of a particular atom. So there are different kinds of capacitors. The most simple capacitor is the so-called electrostatic, also called the parallel plate capacitor. And in this type of capacitor, you have two metal plates that are separated by an electrically insulating material, which is also called the dielectric. So now as you apply a potential to the two metal plates, which act as the electrodes, charges accumulate on these metal plates. Okay, so basically there are positive charges on the metal plate, which is connected to the plus pole of the voltage source, and there are negative charges which are accumulating on the metal plate, which are attached to the negative pole of the voltage source. So now, how many charges do actually accumulate, and how does that relate to actual capacitance? So that depends on a number of factors. So one factor is the type of the dielectric that you use. In particular, the polarizability, which is associated with the so-called dielectric constant of that particular dielectric. So generally, the higher the dielectric constant of the dielectric, the more polarizable that dielectric is, and the more charges can therefore be separated. For that reason, the more charges are actually accumulating on the metal plates. So the dielectric constant is usually given in form of a relative dielectric constant, whereby relative means the dielectric constant relative to the dielectric constant of the vacuum. So pure vacuum has the lowest dielectric constant possible. And this is simply because vacuum doesn't contain matter. And for that reason, vacuum cannot easily be polarized. Okay? So if we set a pure vacuum to have a dielectric constant of 1.0, then we can measure all the dielectric constants of all the other of materials relative to the dielectric constant of the vacuum. So for example, air, which is almost vacuum because there are few particles, atoms present in the air, has a dielectric constant of 1.0006. Okay, so for instance, paper has a dielectric constant of 2.5 to 3.5, glass about 3 to 10, mica 5 to 7, wood 3 to 8, and metal oxide powders 6 to 20. So generally, if you wanted to produce electrostatic or parallel plate capacitor with a high capacitance, you would choose a dielectric which has a dielectric constant as high as possible, yet remain electrically insulated. Okay. So therefore, the nature of the dielectric strongly influences the capacitance. Okay. So now capacitance is given generally as the number of charges that are on our capacitor plates over the voltage. Okay, so basically the more charges that we can accumulate it for a given voltage, the higher our ability to store charge is, and the higher the capacitance is. So the capacitance is therefore proportional to the number of charges for a given voltage, which is proportional to the dielectric constant of the dielectric. Okay. So now this is an intrinsic, the dielectric constant of the dielectric is an intrinsic property, but a capacitor is naturally a device which has certain dimensions. Okay, so the capacitor plates, they have a certain area. Okay, and these capacitor plates are separated by a specific distance. Okay, therefore a specific capacitor as a device has a capacitance also which is proportional to the area of the metal plates. Okay, so that makes sense. So the larger the capacitor plates are, the more surface we have available to store charge. Okay. On the other hand, the capacitance is inverse proportional to the distance, and so that means the closer we bring our plates together, the larger our capacitance becomes. Okay, so we can produce a parallel plate capacitor basically two ways. So we know so-called axial lead type capacitors. So in this case, we have actually two metal foils that are separated by a sheet which contains the dielectric material. And then basically that sandwich of three thin materials is basically just rolled up to form a cylinder. Okay. Of course, you would like to keep the thickness of your dielectric material as small as possible in order to achieve the greatest capacitance possible. So another form of capacitor device is the radial lead type. So in this case, you have actually two wires, as you see here, and you have actually branches that branch out from these wires. Okay, and in between the branches that are part of the different electrodes, you have your dielectric material. So a capacitor is inherently an energy storage device because capacitance is directly related to energy. So the exact relationship is given here. So the energy is given by a half times the capacitance times the voltage square, which is equivalent or equal to a half times the number of charges stored times the voltage. So now which level of capacitance can you actually produce in such an electrostatic capacitor? The capacitance that you can reach is typically in the order of microfarads. So farads is the unit of a capacitance, and micro means then that you can store charges in the order of 10 to the minus 6 farads. So generally, the amount of energy that you can store in an electrostatic parallel plate capacitor is pretty small. However, you can charge and discharge such a capacitor very quickly. So despite having a low energy density inside of your capacitor, you have access to this energy very quickly, and that leads to high power density. So now when we have a supercapacitor, then we have a type of capacitor that can store a lot more charges, therefore a lot more capacitance can be achieved. And for that reason, we can also store a lot more energy in a supercapacitor in comparison to an electrostatic capacitor. So what are the design principles of a super capacitor? So in this case, we have a high surface area material as an electrode material, which is electrically conductive. And most supercapacitors are using high surface area carbon materials, for example, activated carbons. And then that high surface area activated carbon is in contact with an electrolyte that contains the ions. So we basically have now two activated carbon electrodes, which have a high surface area and are electronically conducting. And these activated carbon electrodes are separated by an electrolyte, which acts as the dielectric. Okay, so that electrolyte is not electronically conducting. It is only ion conducting. So now what happens as we apply a voltage to such a capacitor? Well, from the voltage source, the charges will start to go into the electrodes, okay? And the surface of the carbons will get charged. Okay, at the positive electrode, we will have positive charges on the carbon pore surfaces. And at the negative electrode, we will have negative charges on the carbon surfaces. Okay, so now the positive charges, they attract the negatively charged ions that are within the electrolyte. And the negative charges on the pores, they attract the positive ions, the cations, which are within the electrolyte. Okay, so now what you form on the carbon surface is what's called an electric double layer. Okay, layers of positive charges, which are counterbalanced by layers of anions on the pore surface, and layers of negative charges on the pore surfaces, which are counterbalanced by layers of positive ions that came out of the solution. Okay, so now, of course, you're also having charges stored within your electrode materials. But you have now or the ability to store a lot more charges in comparison to a parallel plate capacitor. That is because our electrode is now not a flat surface, but it's actually a highly curved surface. So we have a high surface area material as our electrode, and therefore we have orders of magnitudes more surface area available. Consider that activated carbons can have surface area in the order of hundreds to several thousands of square meters per gram of a material. So if you fabricate an electrode from 1 gram of an activated carbon material, we may have available an internal surface area of several hundred to several thousand square meters. And we can use, in principle, all that surface area in order to make our electric double layer form. Okay, so what does that mean for the capacitance? Well, the formula for the capacitance of a supercapacitor is in principle the same as the formula for the capacitance of parallel plate capacitors. So we have again that the capacitance is the number of charges over V, which is equal to the dielectric constant of the medium times the area over the distance. Okay, so now our area is orders of magnitudes larger in comparison to a simple electrostatic capacitor. Therefore, the capacitance is orders of magnitudes larger. Okay, so this is the first factor. However, there is also another component to this. The capacitance is also inverse proportional to the distance. Okay, and by distance we mean basically the distance between the positive charges and the negative charges. Okay, so now a single electrode with a single double layer actually represents a single capacitor, because we have positive charges and negative charges that are separated by a specific distance. Okay, so the negative charges cannot hop basically into the electrode material. Therefore, we still have capacitance and not a redox process. Therefore, they must be separated by a certain distance from each other. Okay, but that distance is now, of course, extremely small. It's in the order of a fraction of a nanometer. Okay, because the distance between, for example, a positive charge on the pore surface and an anion adjacent to the pore surface is just a fraction of a nanometer. Okay, therefore, not only we have a much larger area available, also the distance between the charges is orders of magnitudes smaller. Okay, and that is the second reason why in supercapacitors we can achieve capacitances which are many orders of magnitudes larger in comparison to parallel plate capacitors. So while parallel plate capacitors typically can achieve capacitances in the order of microfarads, we can achieve capacitances in the order of farads to hundreds and even thousands of farads available. Okay, so now what is in this case the dielectric constant of the dielectric? So in this case, the dielectric constant is determined by the dielectric constant of the electrolyte. Okay, So the dielectric constant of the vacuum is multiplied by the dielectric constant of the electrolyte, and the two, then the combination of the two then also contributes to the overall capacitance. All right. So another point that we need to consider is when we have a supercapacitor, then we always actually have two capacitors in series, because we have two double layers to consider. One at the positively charged electrode, and here one at the negatively charged electrode. So that means that the overall capacitance of our capacitor is actually, well, 1 over the capacitance at the positive electrode plus 1 over the capacitance of the negative electrode. That gives 1 over the capacitance of the overall capacitors. Okay, so we have two capacitors in series, so therefore the two electrodes, the capacitance of the two electrodes add up accordingly. And this formula represents the formula for capacitors which are actually in series relative to each other. Okay, so here we actually see how the potential drops across the capacitor. So we have a potential drop according to the first capacitor, and then throughout the bulk electrolyte, this area here, the potential essentially remains constant, and then they have an additional potential drop within the second double layer, and then the sum of these two gives the overall difference in potential that we measure across the entire capacitor. All right, so now these are the principles of super capacitors. We can use different kinds of carbon materials in order to fabricate supercapacitor, but we can also use different electrolytes. So we can distinguish between supercapacitors that use aqueous electrolytes and supercapacitors that use organic electrolytes. So the aqueous capacitors have the advantage that water has actually a very high dielectric constant, a higher dielectric constant in comparison to organic electrolytes. However, aqueous electrolytes have the disadvantage that you can only apply a voltage of a little bit more than 1 volt to that supercapacitor. If you apply a higher voltage, then you start to get water electrolysis. Okay, so this is a limitation of aqueous super capacitors in comparison to organic electrolyte supercapacitors. I should also mention here that in comparison to parallel plate capacitors, the voltage is more limited, just because also an organic electrolyte will undergo electrolysis at relatively low voltages. You can only apply a few volts, so 3 to 5 volts, but that's about the maximum. But when you have a parallel plate capacitor, you can apply much higher voltages. However, also not infinitely high voltages, because at a certain voltage, also your dielectric in your parallel plate capacitor will break down. So this is called the dielectric breakdown voltage of the dielectric. But it's this only typically occurs at much higher voltages in the orders of hundreds to thousands of volts. Okay. Still, despite you can apply higher voltages to parallel plate capacitor, the capacitances are still much smaller just because of the higher internal surface area of supercapacitor electrodes and the, well, sub-nanometer distance between the charges in the electrodes and the counter ions. All right, so you see here a number of carbon materials listed that you can use as supercapacitor electrodes. You see here their surface areas. You see that they generally vary between approximately well, 400 and nearly 4,000 square meters per gram. You see here the associated capacitances that you can reach. So these capacitances, sorry, are so-called specific capacitances. So specific capacitance means capacitance in farad per gram of the material, or the capacitance in farad per cubic centimeter of a material. But you see, generally you can achieve very high capacitances. So in just 1 gram of carbon material, you can achieve a capacitance of 200 farad. You can easily imagine that you can fabricate capacitors out of multiple grams of electrode material that gives you then capacitors that have capacitances in the order of several thousand farads. What you also see is that the capacitances that you can achieve in aqueous electrolytes are generally higher than those in organic electrolytes, just because of the higher dielectric constant that you can achieve in aqueous electrolytes. However, not necessarily you can store more energy in an aqueous electrolyte. Actually, usually you can store more energy in a supercapacitor with an organic electrolyte, because the energy, as we saw previously, is changing according to the formula. Energy is a half CV square. So because of that square behind the V, the voltage that you can apply actually is really significant. Okay, so the capacitance only increases linearly with the dielectric constant, but it increases with the square of the voltage. So therefore, high energy applications, organic electrolytes are typically more useful than aqueous electrolytes. So that specific capacitance in farads per gram is related to the actual capacitance of the entire device through this formula here. So the specific capacitance is 4 times the capacitance of the entire capacitor over the mass of the two electrodes. So that formula applies here if the capacitor is symmetric. So that means that both electrodes produce or are assumed to produce the same capacitance, so that the capacitance is Ci over a half, and then the two capacitances add up according to this formula here. 1 over C is 1 over C1 plus 1 over C2, whereby C1 and C2 are assumed to be the same. In this case, it's also assumed that the two electrodes have equal mass. So if you want to determine a specific capacitance, you measure the capacitance of your capacitor, okay, divided by the mass of the two electrodes and multiplied by force. This gives you the specific capacitance at a particular electrode. All right, so how can you determine capacitance experimentally? So there are two basic techniques that you can use. So you can determine capacitance from so-called galvanostatic charge discharge curves, in which you keep the current constant, or you can determine capacitance from cyclovoltammetry curves, in which you keep the scan rate constant. So generally, the capacitance is the current over the change of the voltage over the time. So when you collect galvanostatic charge discharge curve, then in ideal capacitor, the voltage changes linearly with the time until you reach the final voltage. For example, 2.5 volts in a capacitor with an organic electrolyte. When you then discharge your supercapacitor, your voltage will decrease linearly over the time until you arrive back at 0 volts. And you can repeat this over multiple cycles. So here you just see a second cycle, third cycle, fourth cycle, and the fifth cycle. And ideally, the curves are always identical. So that tells you that your capacitor actually doesn't change over the time as a cycle of multiple times. Particularly, your capacitor doesn't deteriorate over the time. Okay, so now how can you determine the capacitance? So the capacitance is nothing else but your constant current that you know over dV over dt, which is nothing else but the slope of the line within a galvanostatic charge discharge curve. Okay, so you only need to determine the slope of this line multiplied with the constant current that you know, then you actually have your capacitance within your capacitor. So not always the capacitors behave completely ideal. So you see this actually here in this graph. So you see actually here that initially the potential jumps before the curve approximately follows a line, even though the line is not exactly a straight line as it should be. In the ideal case, it's somewhat bent. And this is because of internal resistance within the capacitor. So when you discharge, you see also here that there's a voltage drop, which is due to internal resistance, followed by the decrease of the voltage over the time. So this capacitor here represents a capacitor which is ideal, meaning you have no internal resistances to deal with. You also have no redox processes taking place at all. This is a more realistic case in which you have internal resistances within your capacitor. Okay, now when you have measured your capacitance of your overall capacitor, you can determine the specific capacitance or specific electrode using this formula here for I dt over dV over m, which follows naturally from the combination of this formula together with this formula here. So this is how you can determine the capacitance using galvanostatic charge-discharge curves. So another method is to determine the capacitance from cyclovoltammetry curves. So in this case, you keep the scan rate constant. That means the change of the voltage in a particular time unit. So for instance, a scan rate could be 10 millivolts per second or 50 millivolts per second or 100 millivolts per second. And you would again change the voltage at that scan rate up to a particular final voltage. And what you measure in this case is not the voltage like you do in the galvanostatic charge-discharge curve, but the current. Okay. So an ideal capacitor, you will have a cyclovoltammetry curve which follows an exact rectangle. So as you start scanning at a particular scan rate, you will measure a certain current which will remain constant until you reach the final voltage. If you discharge, then the same current will flow into the opposite direction. So in this example here, for instance, our current flows at a rate of 200 milliamps, okay, and keeps approximately constant. Okay. Now, as we basically scan the opposite direction, well, we will have approximately the same current, but flowing with the opposite direction at 200 millivolts, okay, until we have gone back to the original voltage. So now the scan rate is nothing else but dV over dt. So the capacitance is I over dV over dt. So therefore, we can determine the capacitance by actually just integrating an area underneath the cyclovoltammetry curve where the current is approximately constant, okay, over a certain potential window. So that gives you then the number of coulombs which are being stored, and then you only need to divide the number of coulombs over the voltage difference, which in this case would be just the voltage difference between this point and that point here, which in our example shall be 1 volt in order to give the capacitance. So this integral would give 3.195 coulombs, and that divided by 1 volt would then give 3.195 farads. All right, so this would be the second way in order to determine capacitance of a super capacitor. So I mentioned previously that you can have internal resistances within your capacitor, which is naturally not ideal, and there are actually two types of resistances. That's the so-called equivalent series resistance, and that's the so-called parallel resistance. So the equivalent series resistance is essentially the sum of the series resistances within your capacitor. So that is the resistance of the electrical resistance of the electrolyte plus the electrical resistance within your electrode itself, plus all the contact resistances. Okay, for example, the contact resistance associated with the contact between the supercapacitor electrode material and the current collector. Okay, so we have basically a circuit is shown here. So here we have an ideal capacitor, which has no series resistance, but we can model a real-world capacitor by placing a resistor in series behind our ideal capacitor. Okay, so these two in combination would then model a real-world supercapacitor with a series resistance. All right, so now we can easily determine that equivalent series resistance from the so-called IR drop of galvanostatic charge and discharge curve. You see that when we start a cycle, then the voltage jumps to a certain level, okay, before it actually increases in a linear way. And when we reverse the current, then again we get a potential jump. And that is because the IR drops. So essentially the voltage difference that we measure here is equal to the constant current over the equivalent series resistance. And when we solve this equation just for the equivalent series resistance, then the equivalent series resistance is equal to the constant current over that delta V here. So this is how you can measure the internal series resistance for a supercapacitor very easily. All right. So now, in addition to that, we have the so-called parallel resistance, and the parallel resistance resembles nothing else but the current leakage through a supercapacitor. So when you charge a supercapacitor, your supercapacitor will not hold these charges for an infinitely long time in an open circuit, but it will self-discharge at a certain rate, because statistically charges can actually also go across the electrolyte from one electrode to the other at a certain rate. Okay, and that is because the electrical resistance of your electrolyte in between the electrodes is high, but it's not infinitely high. Okay, so therefore we can model that by assuming that we have an ideal capacitor here in our circuit, and parallel to that we have a resistor, which is a finite resistor through which, well, there is some leakage current. Okay, so in an ideal supercapacitor, this R would be infinitely high, but in a real world capacitor, this parallel resistance would have finite value. So the current leakage within a supercapacitor occurs according to an exponential term, which is given here. So the voltage is equal to the initial voltage at full charge times e to the power of minus t to the capacitance times the parallel resistance. Okay, so we can take the logarithm of that, then ln v is as t times ln v0 times c are parallel. So if you plot ln v versus the time, then you can determine the parallel resistance just from the slope of the respective line. In practice, you may not get a completely straight line because there are other processes that can occur as well. For instance, Faraday processes or multiple parallel resistances that occur because of the irregularities within your electrode material, for instance, different pore sizes, etc. The parallel resistance also depends on temperature. So generally, when you go to higher temperature, then the resistance becomes smaller as more electrons can statistically actually leak through the electrolyte to the opposite electron. All right. Now, how can we determine how efficiently our supercapacitor works? So there are two major performance criteria to consider here. One is the so-called Coulomb efficiency, and the other one is the energy efficiency. So these two are actually not the same, so we have to distinguish them carefully. So what do we mean by Coulomb efficiency? By Coulomb efficiency, we mean nothing else but the number of charges which we can pump into the capacitor versus the number of charges that leave the capacitor during discharge. Okay, so that difference is the number of charges that basically got stuck in the capacitor irreversibly, determining the so-called Coulomb efficiency. Okay, so the number of coulombs are nothing else but current times time. So when we perform a galvanostatic charge-discharge experiment, we keep the current constant. Okay, so the current is constant while we charge and discharge. So therefore, the Coulomb efficiency is given by I times the time that we need to discharge over I times the time that we need to charge, but I, of course, cancels out, the current cancels out, so the Coulomb efficiency is nothing else but the time of discharge over the time of charge. Okay, so the time of discharge is always equal or smaller than the time of charging, just because we cannot achieve a Coulomb efficiency of higher than 100%. All right. So now, how do we determine the energy efficiency? So the energy is basically given by the voltage times the time times the current. Okay, so voltage times the time is nothing else but the integral underneath a charge or discharge curve respectively. Okay, so therefore, if I actually measure the integral over underneath the charge curve, okay, and multiply this with the constant current with which I charge and which I know, then I have determined the energy that are actually used in order to charge my capacitor. Okay. So now the integral under the discharge curve is nothing else but the voltage times the time during discharge. And when I multiply that with the constant current with which I discharge, then I measure actually the energy that I retrieve from the capacitor as I discharge it. Okay, and therefore just the ratio of the integral underneath the discharge curve and the integral underneath the charge curve give me my relative energy efficiency in percent. Okay, I can also calculate easily the number of joules that I have lost. Okay, if I actually subtract the energy derived from the integral underneath the discharge curve from the energy derived from the integral under the charge curve. All right, so last but not least, let us look a little bit more closely at how can we actually model the electric double layer that gives rise to the capacitance. There are actually three basic models known that differ somewhat in complexity. So the most simple model is the so-called Helmholtz model. So this Helmholtz model assumes that we have so-called compact double layer of ions on the surface which is charged. Okay, and there is a distance between the centers of the charge which is actually uniform. Okay, so now in reality, this is somewhat oversimplified just because of temperature, and these effects now are taken into account by the so-called Chapman model, okay, which assumes a so-called diffuse layer instead of a compact layer. Okay, so the Chapman model assumes that because of thermal motion, the ions do not lie rigidly and fixed on the surface, but they somewhat bounce back and forth from the surface. Therefore, we actually have a broader, more diffuse double layer in which we do not only have ions, but also solvent molecules in between these ions, and the solvent molecule also can coordinate to these ions. Okay, so now the Stern model, it basically combines these two ideas, saying that we have both ions that are actually lying desolvated on the surfaces. Okay, so we have a so-called Stern layer here, but in addition to that, we also have a diffuse layer, so that the overall capacitance is actually given by 1 over the overall capacitance being equal to 1 over the capacitance of the Helmholtz layer plus the overall the capacitance of the diffuse layer. Okay. So this model is, of course, still relatively simple because it assumes flat surfaces. So in reality, we of course do not have flat surfaces because we work with activated carbons as electrode materials. These surfaces are often highly curved. And of course, we also have the pore sizes to consider. So we have a pore size distribution. And the ions, of course, do not fit equally well in these different pores. So they're actually space constraints. Okay. So further, also the nature of the pore surfaces need to be considered. For instance, the hydrophobicity, the hydrophobicity, how well the electrolyte can actually wet a particular surface. So that also influences the double layer, the nature of the double layer that forms on the particular surface. So the reality is even significantly more complex than what these three models tell us. Nonetheless, these three models work reasonably well to at least roughly describe the electric double layer. All right, so this is what I wanted to tell you about supercapacitors. We have actually no more material to cover. So this was the last lecture of this course, but we can of course use still time for questions. So are there